I'm Adam from RFOXiA from our real lab. Today we are answering the question every embedded developer eventually faces at the worst possible hour. What actually happens when two sensors on the same I2C bus share an address, and how do you stop it from happening again? Let me describe a situation that is more common than it should be. You are building a project, you need a temperature sensor, you pick one, you wire it up, it reads correctly, everything is fine. Then you need a pressure sensor, different chip, different function, same I2C bus. Because that is the point of I2C, you share the line, you wire it in. Now one of them is giving you garbage data, sometimes both of them are. You check your code, you check your wiring, you reset the board, you read the datasheet for the third time, nothing changes. What you are looking at is an I2C address collision. And if you have never hit one before, it is a genuinely confusing experience because nothing about the failure mode tells you what the actual problem is. Here is what is happening. I2C is a two-wire communication protocol, one line for data, one line for clock. Multiple devices share both wires and they take turns talking based on a 7-bit address. The controller sends a start condition, puts an address on the bus, and whichever device recognizes that address responds. Simple, clean, elegant, even. The problem is that the 7-bit address space gives you 128 possible addresses, and manufacturers do not distribute them evenly across the universe of devices. They assign default addresses based on the application domain the sensor was designed for. So you get categories of sensors, environmental, motion, analog converters, that cluster around certain address ranges, and when you are building a project that needs multiple sensors from similar categories, you will eventually find two of them sitting at the same default address. When that happens, both devices respond to the same address simultaneously. They pull the data line in conflicting directions. The controller reads the superimposed result of both responses at once, which is not the data from either device. It is electrical noise with a header, and your code, which was written assuming one device per address, has no framework for understanding what went wrong, so it either logs the corrupted value or it hangs. The conventional approach to resolving this is address remapping. Many sensors expose one or two physical pins, labeled ADR or ADR, that let you change the I2C address by tying them high or low. Instead of address 0x76, you get 0x77. That gives you two options per device. If you have two of the same sensor, you set one to each option. Problem solved, except it is not actually solved, it is deferred. Because the moment you need a third sensor of the same type, or two different sensors that happen to occupy the same address range regardless of their ADDR pin state, you are out of options without introducing additional hardware. I2C multiplexers are the typical answer at that point. A multiplexer sits between the controller and the sensors and lets you selectively enable subsets of the bus, effectively creating isolated address spaces. This works. It also adds another component, another I2C device with its own address that you have to manage, additional firmware logic, and additional points of failure. I want to be precise about what the multiplexer approach is doing. It is not solving the address conflict, it is routing around it. The conflict still exists. You are just making sure the conflicting devices are never active on the bus at the same time, which means you also cannot read them at the same time. If you need synchronized data across sensors, motion and pressure simultaneously, for example, for a drone altitude controller, you are now managing timing and sequencing between bus segments to approximate the simultaneous read you needed. This is not simpler. This is the complexity of the original problem plus the complexity of managing the multiplexer. And here is the thing that bothers me about all of this. The address conflict is not a physics problem. It is not a fundamental constraint of I2C as a protocol. It is a consequence of how devices are brought to market individually, with no coordination between manufacturers about address allocation across the full system. A developer might eventually assemble. The developer inherits the coordination problem because the industry did not solve it upstream. So when we were designing the MultiNav Pro Plus sensors module, the question was not how to manage address conflicts between the 7 sensors on the board. The question was why those conflicts should exist at all if you are designing the full system yourself. 7 sensors on one board means you control the entire I2C address map before a single line of user code is written. The BMI 270 from Bosch Sensortec handles the accelerometer and gyroscope. The TMAG 5273 from Texas Instruments handles the magnetometer. The LPS 22HH from ST Microelectronics handles air pressure. The MVH 4003D from MEMS Vision handles humidity and temperature. The ZAMOD 4510 from Renesas handles air quality. These are not arbitrary choices. They are selected partly for their performance and partly because their address spaces do not overlap with each other. There is no conflict to resolve because the conflict was avoided at the selection stage. Every sensor. So that is the architecture. One bus, 7 addresses, no collisions, no multiplexers needed. Now let me show you the actual hardware and walk through what is physically on this board. This is the Multinav Pro Plus Sensors module, 7 sensors on one board: accelerometer, gyroscope, magnetometer, temperature, air pressure, humidity and air quality, all of them selected and laid out so that none of their I2C addresses conflict with each other. The entire coordination problem is handled before your firmware touches it. The motion and environmental halves of this module serve completely different purposes, which is why they needed to coexist without interfering. The BMI 270, the TMAG 5273 and the LPS 22HH give you the orientation and altitude data a drone flight controller needs at high update rates. The temperature, humidity and air quality sensors give you the environmental context that turns raw telemetry into useful field data. These are the specific chips on the board: BMI 270 from Bosch Sensor Tech for motion, TMAG 5273 from Texas Instruments for magnetics, LPS 22HH from ST Microelectronics for pressure, MVH 4003D from MEMS Vision for humidity and temperature, ZMOD 4510 from Renesas for air quality, each one selected in part because its default I2C address does not collide with any other device on this board. One I2C line, 7 devices. Every sensor has a dedicated address, which means the controller can address each one individually without ambiguity. No multiplexer, no address remapping, no ADDR pins to pull high or low. You wire SDA and SCL and the bus works exactly as the I2C specification says it should. The board is 24 by 18 millimeters, that is the size of a large postage stamp. Getting 7 sensors onto that footprint without compromising their individual performance, their address isolation, or their I2C routing required actual layout work. The compactness is not a marketing point, it is an engineering constraint that was met. Real-time data across all 7 channels simultaneously. Because there are no address conflicts and no multiplexer sequencing, you can query every sensor in a single I2C transaction loop and get synchronized readings, temperature, pressure, motion state, and air quality at the same timestamp. That is what CleanBus architecture enables. The use cases extend well beyond any single application. Drones use the motion and pressure channels. Environmental monitoring nodes use the humidity, temperature, and air quality channels. Wearables use a subset of both. The common thread is that all of these applications benefit from the same thing, a sensor system that works the way it is supposed to, without the developer spending time managing problems the hardware should have already solved. Each sensor by its address, you get back exactly the data you asked for. Nothing interferes with anything else. The Multinav Pro Plus Sensors module assigns every sensor its own dedicated I2C address on a single shared line, so you spend your weekend building your project instead of debugging a bus collision at 2 a.m. That is what a solved problem looks like. Not a workaround, not a multiplexer, not an ADDR pin you have to remember to pull high. A system where the correct answer was baked in before you received the hardware.